Let's do Brahmanad. Om. Om. Shanti. 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 Swastha. Dear student, now I will discuss about a new chapter, that is your solid state. It is a physical state of a matter in which the matter having definite shape and definite volume. Classification of solid. Classification of solid. Solid are classified into two types. One is your amorphous, another is your crystalline. First is your amorphous, second is your crystalline. There is a large difference between amorphous and crystalline solid. It is also an important 2 or 3 mark question. This is your amorphous, this is your crystalline. In case of amorphous, the shape is irregular, but in case of crystalline, the shape is definite. That means in crystalline solid, it shows definite characteristics, geometrical shape. The second point is surface cleave is irregular. In case of amorphous, the surface cleave is irregular. On the other hand, surface of cleave is plane and regular in case of crystalline solid. In case of amorphous solid, it gradually softens over a range of temperature, but in case of crystalline solid, it melts at a sharp and characteristic temperature. Amorphous solid do not have definite heat of fusion. On the other hand, crystalline solid having definite and characteristic heat of fusion. Amorphous solid is isotropic in nature. On the other hand, crystalline solid is anisotropic in nature. Amorphous solid is a pseudo-solid or supercooled liquid. On the other hand, crystalline solid are the true solids. In case of amorphous solid, only short range order in arrangement of constituent particles. On the other hand, in crystalline solid, long range order of arrangement of constituent particles. These are the difference between amorphous solid and crystalline solid. Some examples of crystalline solid are NaCl, KCl, MgCl2 like this. Some example of amorphous solid are glass, next is plastic, rubber, starch, protein. These are the examples of amorphous solids. Next I will explain about the classification of crystalline solid. Depending upon the binding force, crystalline solids are classified into 4 types. One is your molecular crystal, second is covalent crystal. It is also called atomic crystal. Third is metallic crystal. Fourth is Ionian crystal. There are 4 types of crystalline solid. At first, I will discuss about the molecular crystal. What is the molecular crystal? When the lattice point in crystal are occupied by small molecules which are held together by weak van der force of attraction or hydrogen bond, then such type of crystal are called molecular crystal. For example, solid carbon dioxide. Next example is iodine. Next is your sugar, etc. These are the examples of molecular crystal. Later I will discuss about the meaning of lattice point. What are the properties of molecular crystal? First point is it is generally soft. Second point is low melting point. Low melting point. Third is also low boiling point. Next point is volatile in nature. Volatile in nature. Next point is low heat of vaporization. Low heat of vaporization. Next point is bad conductor of electricity. Bad conductor of electricity. These are the properties of molecular crystal. Next I will discuss about the covalent crystal. In covalent crystal, when the lattice points in crystal are occupied by atoms which are held together by covalent bond, then such crystals are called covalent crystal. Remember one important point. In molecular crystal, the lattice points are occupied by small molecule and the force by which the molecules are held together, that is your van der force, that is your weak van der force or hydrogen bond. But in case of covalent crystal, the lattice points are occupied by atoms and the force which connected to the atoms through a bond, that is your covalent bond. So we can think that when the lattice point in crystals are occupied by atoms which are held together by covalent bond, then such crystals are called covalent crystal. Example is your diamond, graphite, silicon carbide, quartz. These are the examples of covalent crystal. What are the properties of covalent crystal? First point is covalent crystals are hard. Next point is high melting and boiling point. High melting and boiling point. Next point is high heat of fusion. High heat of fusion. Next point is these are insulator except graphite. Except graphite, the covalent crystals are insulator. These are the few properties of covalent crystal. Next I will discuss about the metallic crystal. When the lattice point in crystals are occupied by positively charged metal ions emerged in a sea of electrons and are held together by metallic bond, then such crystals are called metallic crystal. Obviously, in metallic crystals, the positive charged metals are present and these are placed in the lattice point of the crystal and these are held together by metallic bond. The examples of metallic crystals are iron, nickel, copper, silver, etc. What are the properties of metallic crystal? The properties of metal crystals are: first point, metal crystals are usually hard and rigid. Second point is high melting point and boiling point. Metal crystals having high melting point and boiling point. Next point is metallic crystals are good conductor of heat and electricity. Next point is metallic crystals are bright metallic luster. Next point is metallic crystals are malleable and ductile. Metal crystals having moderate heat of fusion. These are some few points regarding about the metallic crystal. Next I will explain about the Ionian crystal. When the lattice points in a crystal are alternatively occupied by oppositely charged ions and are held together by electrostatic force of attraction, then such type of crystals are called Ionic crystal. Examples of Ionic crystals are NaCl, KCl, next is your KNO3, etc. These are the examples of Ionic crystal. The properties of Ionic crystals are: first point is Ionic crystals are hard and brittle. Next point is Ionic crystals having high melting point and boiling point. Next point is Ionic crystals having high heat of vaporization. Next point is Ionic crystals are poor conductor of electricity in solid state, but it acts as a good conductor of electricity in fused or molten state or in aqueous state. Suppose I want to draw the diagrammatical representation of an Ionic crystal. Suppose I will take NaCl. How can I draw the crystal structure of NaCl? This is the structure of sodium chloride. Here, suppose Na plus ion is present, then this is your Cl minus, this is your Na plus, next this is your Cl minus, this is your Na plus, this is your Na plus, this is your Cl minus, this is your Na plus, this is your Cl minus. The positive ion and negative ions are arranged in an alternative manner. This is your Na plus, this is your Cl minus. Look at that. Your Na plus ion is present, then Cl minus ion is present, then Na plus ion is present, then Cl minus, then Na plus, this plus, this is your Cl minus, this is your Na plus, this is your Cl minus. This is your Cl minus, this is your Na plus. Here also Na plus is present, this is your Cl minus. In NaCl ionic crystal, the Na plus and Cl minus are arranged in an alternative manners. These are all about the classification of crystalline solid. Next I will discuss about the meaning of lattice point. What is the lattice point? Next I will teach you what is a crystal lattice. Next I will teach you what is a unit cell. The lattice point is the position occupied by the constituent particles in a crystal. That means the constituent particle may be atom or ion or molecules. So we can write the position occupied by the constituent particles. Constituent particles may be atoms, molecules or ions in the crystal. In the crystal are called lattice point. Next is your crystal lattice. Crystal lattice is also called space lattice. What is the meaning of crystal lattice? The regular arrangement of the constituent particles at different points in a three-dimensional space is called space lattice or crystal lattice. Next is your unit cell. The smallest three-dimensional portion which repeats itself in different directions to produce the complete space lattice is called unit cell. Let me explain by the help of an model. This is your one type of model. Look at that. You can arrange the lemon in different directions like this. Suppose I want to arrange here one lemon like this, in upper direction, in front direction, in back direction, in left direction, right direction, as your choice. You can arrange the lemons in different way to make a space lattice or crystal lattice. Here you can also arrange another lemon to produce another cubic type of arrangement. Look at that. This is the position in which the constituent particles are present. Suppose think that the lemons are atom or ions or molecules. They are occupied in a particular position in the crystal. These positions are called lattice point. That means this position is one lattice point, this is your one lattice point, this is the another lattice point, these are the lattice point. The position in which the atom or ions or molecules are placed in a crystal, that is called lattice point. In this position, the lemon is placed. It acts as maybe an atom or ion or molecule, but it is placed in this position in the crystal lattice, so it is called one lattice point. It is also one lattice point, it is also another lattice point, like this. That means where the atom or ion or molecule are present in the crystal lattice, that is called lattice point. The totally regular arrangement of the constituent particle at different points in the three-dimensional space is called space lattice. That means this total system is generally called crystal lattice. You can arrange the lemon in a long distance, in a long orderly arranged manner, as your choice. But the total crystal is considered as said to be space lattice or crystal lattice. If you think about the smallest portion that is your smallest three-dimensional portion, then I can find that this is your smallest three-dimensional portion. Look at that, this is the smallest three-dimensional portion. It is called unit cell. Remember, the smallest three-dimensional portion which repeat itself in different direction to produce the complete space lattice is called unit cell. That means by repeating this portion, we can able to form the space lattice, that is your crystal lattice. Suppose I will take here, then I will arrange the other cubic in this place, and also arrange in this place, and also arrange this cubic system in the front side and back side also in the bottom side. Like this, you can repeating this unit, you can able to form a large crystal that is considered as space lattice or crystal lattice. Look at that. This is your one type of model to explain the term lattice point, space lattice and unit cell. Let me explain by diagrammatical representation. This is your completely said to be crystal lattice. You can also extend the portion in left side, right side, top side, bottom side, back side, front side, as your choice. But this is considered as a crystal lattice. If it is considered as a crystal lattice, then look at that. This is the smallest portion by which we can able to form the space lattice. This smallest three-dimensional portion is called unit cell. By repeating this smallest three-dimensional portion, we can able to form the crystal lattice. So this is your said to be unit cell. This smallest portion is said to be unit cell, and the complete diagram considered as the crystal lattice. Suppose I will place the constituent particle, that is your ion, atom or molecule, in this position of the crystal, then this is said to be lattice point. Suppose here I will be placed a atom or ion or molecule, then this is also called lattice point. That means in the crystal, in which place the atom or ion or molecule will be placed, then that place is called your lattice point. Suppose I will place a atom or ion or molecule here, then this position is also considered as the lattice point. Lattice point means the position occupied by the constituent particle, that is atom, ion or molecule, in a crystal are called lattice point or lattice site. Next I will discuss about the types of unit cell. Suppose this is your an unit cell. Look at that. If in this unit cell, if these are the said to be lattice point, in case of molecular crystals, these lattice points are occupied by molecules, and the force of attraction by which these molecules are held together by each other is must be a weak van der force of attraction or hydrogen bond. Then such type of crystals are said to be molecular crystal. In case of covalent crystals, these lattice points are occupied by atoms and there must be a force which held the atoms, that is said to be covalent bond. In case of metallic crystals, the lattice points are occupied by positive charged metals and there is also a force of attraction between the metals, that is said to be metallic bond. On the other hand, in case of ionic crystals, the lattice points are occupied by ions and there must be a force which is able to hold the ions, that is said to be ionic bond. Generally there are two types of unit cell. One is your primitive unit cell, that is also called simple unit cell. Second is non-primitive unit cell. Primitive unit cell means the constituent particles are present only at the 8 corner of the unit cell. This is your examples of primitive unit cell. Look at that. In this unit cell, the constituent particles are present at the 8 corner of the unit cell. Example is your polonium. In case of polonium, the constituent particles are present only at the 8 corner of the unit cell. Okay. Next is your non-primitive unit cell. In case of non-primitive unit cell, the constituent particles are present at both corner as well as face center, as well as head center, as well as body center of the unit cell. The non-primitive unit cell are classified into different types. One is your face centered cubic, second is your body centered cubic, third is your end centered cubic, another is also that is your edge centered cubic. Next I will explain about what is a primitive unit cell and what are the different types of non-primitive unit cell, that is your face centered, body centered, end centered, head centered. This is your said to be simple unit cell because in this case the lattice points are present at the corner of the unit cell. That means the constituent particles are present only at the 8 corner of the unit cell. So this is said to be a simple unit cell. Next is your non-primitive unit cell. In case of non-primitive unit cell, no doubt the constituent particles are present at the corner of the unit cell. Also the constituent particle present at the face center and also at the body center and also at the head center, like this. Suppose this constituent particle present at the center of the body. This is your center of the body. Look at that. Here one constituent particle present, here another, here also another. That means 8 particles are present at the 8 corner of the unit cell and also another particle present at the center of the body. Then this is your said to be body centroid cubic. Next is your face centroid cubic. There are 6 faces of the cubic. This is your 1, 2, 3, 4, 5, 6. If 6 constituent particles are present at the 6th center of the face along with the 8 constituent particles present at the corner, then the unit cell is said to be face centroid cubic unit cell. That means the structure is look like this. Here one constituent particle present, here second, third, fourth, fifth, sixth. Also, there are 8 constituent particles present at the 8th corner. That is the diagrammatical representation of the face-centered cubic. Next is your end-centered cubic. If 8 constituent particles present at the 8th corner of the cubic, then 2 constituent particles present at the face. That means 2 constituent particles are present opposite face of the cubic. Suppose this is the center of one face, the opposite face is here. This is the opposite face of this face. Now one constituent particle present here and the second constituent particle present here. Then this type of unit cell is said to be end-centered unit cell. Suppose one constituent particle present here, another constituent particle present here. Then this is also said to be end-centered cubic. Suppose one constituent particle present here, another is present here. This is also end-centered cubic. Remember, there must be 8 constituent particles present at the 8th corner of the cubic. Along this, you can think about the other 2 constituent particles. Next is your edge-centered cubic. In edge-centered cubic, the constituent particles are present at the center of the edges. In this unit cell, how many edges? There are 12 edges present. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 edges are present. Look at that. One constituent particle present at the center of the edge. Like that, another constituent particles are present like this. 12 constituent particles present at the center of 12 edges of the unit cell. This is your said to be edge-centered unit cell. Again I will repeat, this is your primitive cell, that is your simple unit cell. Non-primitive unit cells are different type. First is your body-centered cubic unit cell, when an extra constituent particle present at the center of the body, then such type of unit cell are considered as body-centered cubic. Similarly, what is a face-centered cubic? When the constituent particles are present at the center of the face, along with the 8 constituent particles present at the 8th corner of the unit cell, then such type of unit cell are considered as face-centered cubic. Next is your end-centered cubic. In end-centered cubic, 2 extra constituent particles present at the center of 2 opposite faces. In edge-centered cubic, the constituent particles are present at the center of edges of the unit cell. I can draw the simple unit cell like this. This is your simple unit cell. In this unit cell, the constituent particles are present at only at the 8th corner of the unit cell. This is your simple unit cell. Next is your body-centered unit cell. This is your simple unit cell, but when an extra constituent particle present at the center of the body, then that is converted into body-centered unit cell. This is your BCC, body-centered cubic unit cell. This is your SCC, simple-centered cubic unit cell. Next is your face-centered unit cell. This is your simple unit cell. But if 6 constituent particles are present at the center of 6 face, then that is converted into FCC, face-centered cubic unit cell. This is your one face. Your particle present. This is the front face. Here also one constituent particle present. This is your back face. This is the center. Here also one constituent particle present. This is the left face. And this is your center. Here also one constituent particle present. This is the right face. And this is the center of this face. So here also one constituent particle is present. This is your said to be FCC, this is your said to be BCC, this is your said to be SCC. Next is your end-centered cubic unit cell. This is your simple unit cell. Look at that, this face and this face are opposite to each other. Suppose one constituent particle present, the second constituent particle must be present here for the end-centered cubic unit cell. Also, you can also place the two constituent particle like this. This is the left face and this is your right face. These two faces are opposite to each other. So this is also your end-centered cubic unit cell. Suppose I can place one constituent particle at the center of front face and other constituent particle present at the center of the opposite face, that is your back face. Then this is also end-centered cubic unit cell. This is your best example of end-centered unit cell. Next is your edge-centered. This is your simple unit cell. There are 12 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now place the constituent particles at the center of the edge. This is the center of the edge. Here one constituent particle present, here also one constituent, here also another. Fourth number is present here. Next is your this. This is your said to be edge-centered cubic unit cell. These are the different types of unit cell related to the cubic. Next I will explain about the two-dimensional lattices and the unit cell. These are different types. Number one is your square unit cell. Number two is rectangular unit cell. Next is parallelogram unit cell. Next is rectangular with the interior point unit cell. And the fifth number is your rhombus. These are different types of unit cells. If the constituent particles are placed like this, then they can able to form the square unit cell. Look at that. This is the smallest portion. By repeating this smallest portion, we can able to form the crystal lattice. In this case, suppose this is your A, this is your B, this length is A, this length is your B, and this is the angle. Suppose the angle is your L, here L is 90 degree, here here A equal to B. This type of unit cell are considered as square unit cell. Suppose the constituent particles are present like this, then they can able to form the rectangular unit cell. Look at that, this is the smallest portion which look like a rectangular shape. So this is your said to be rectangular unit cell. Suppose this is your A, this is your B, this is the angle. Here A not equal to B and L equal to 90 degree. If the constituent particles are present like this, then they can able to form the parallelogram unit cell. Look at that, this is your parallelogram. Suppose this is your A, this is your B, this is the angle. Here L not equal to 90 degree, A not equal to B. Similarly, I can able to form the rectangular with the interior point unit cell. This is your rectangular with the interior point unit cell. Here one constituent particle present in the center of the rectangular geometry. Here A not is equal to B, but the angle is equal to 90 degree. By repeating this unit, you can able to form the crystal lattice. Next is your rhombus. If the constituent particles are present like this, look at that, here the unit cell look like a rhombus. This is your A, this is your B, then we can write A equal to B, this is the angle. L not equal to 90 degree. These are the different types of two-dimensional unit cell. Look at that. This is the one type of model. Is the unit cell look like square unit cell. By changing the lemon, you can able to form different types of two-dimensional unit cell. You can able to form another unit cell like your rectangular lattice cell, parallelogram unit cell, rectangular with the interior point unit cell, and you can also able to make a model like your rhombus unit cell. By just changing the position of the lemon, you can able to form different types of two-dimensional lattices and the unit cell. Look at that, this is your square unit cell. Because this look like a square, your A equal to B and the angle equal to 90 degree. This is your rhombus type unit cell. You can able to form the rhombus type of unit cell like this. Look at that. Suppose your one constituent particle present, then it can able to form the rectangular with the interior point unit cell. You can also think about the other type of unit cell like this. Next I will explain about the three-dimensional lattices and the unit cell. The unit cells are classified into 7 types called crystal system. First is your cubic, second is that is your tetragonal, third is orthorhombic, Orthorhombic. Orthorhombic is also called rhombic. Fourth is monoclinic. Monoclinic. Fifth is triclinic. Sixth is rhombohedral. Rhombohedral, or it is also called trigonal. Trigonal. Seventh number is hexagonal. Again, the cubic unit cell are different types. One is your simple cubic unit cell. Second is your face centroid cubic unit cell. Next is your body centroid cubic unit cell. Three types. One is your SCC, another is your FCC, third is your BCC. Already I discussed about the end centroid, head centroid, but in case of cubic unit cell, the edge centroid and end centroid are not possible. This can be possible in other crystal system, but the concept is the same. Edge centroid means the extra constituent particle must be present at the center of the edge. End centroid means the extra two constituent particle must be present at the center of two opposite face. In cubic case, there is no possibility of end-centered and edge-centered cubic unit cell. We generally think about the simple cubic unit cell, face-centered cubic unit cell. Next is your body-centered cubic unit cell. But you do not think about the head-centered and edge-centered. In cubic unit cell, A equal to B equal to C, and your alpha equal to beta equal to gamma is equal to 90 degree. Examples are NaCl, KCl, AgCl, CaCl, etc. are the examples of cubic unit cell. Next is your tetragonal unit cell. In tetragonal unit cell, generally two types of unit cell are possible. One is your simple, next is your body centered. That means in case of tetragonal, we can able to form two types of unit cell. One is your simple, second is your body centered unit cell. In this case, A equal to B, not is equal to C. Here, alpha equal to beta equal to gamma is equal to 90 degree. Examples of tetragonal are your TiO2. This is an example of tetragonal. Another examples are SnO2. You can think about the other example like this. Next is your orthogonal or rhombic unit cell. In this case, generally simple unit cell possible, also end centroid, face centroid. Next is your also body centroid unit cell are possible. Yeah, four types of unit cell are possible. One is your simple, second is your end centroid, third is your face centroid, fourth is your body centroid. In this case, A not equal to B, not is equal to C. Here, alpha equal to beta equal to gamma is equal to 90 degree. The examples of orthorhombic unit cell are barium sulfate, FeSO4.7H2O, KNO3, etc. are the examples of orthorhombic unit cell. Next is your monoclinic unit cell. In case of monoclinic unit cell, two types of unit cell are possible. One is your simple unit cell, second is your body centered unit cell. In this case, A not equal to B not equal to C, alpha equal to beta equal to 90 degree, but remember here gamma not equal to 90 degree. The examples of monoclinic unit cell are borax, gypsum, epsom. Next is your triclinic unit cell. Here only triclinic unit cell are possible. Here no possibility of face centered, body centered like this. You can think about only triclinic unit cell. In this case, A not equal to B not equal to C. Here also alpha not equal to beta not equal to gamma. Next is your trigonal. In this case, A equal to B equal to C. In this case also face, body, not such type of unit cell are not possible. Here A equal to B equal to C, and also alpha equal to beta equal to gamma not equal to 90 degree. The examples of trigonal unit cell are KMnO4, sodium nitrate. These are the examples of trigonal unit cell. Next is your hexagonal unit cell. In this case, A equal to B not equal to C. Here also alpha equal to beta equal to 90 degree, and also remember one important point, gamma equal to 120 degree. The examples of hexagonal unit cell are zinc oxide, ice, graphite, quartz. Look at that, this is your cubic unit cell. In this case, suppose this is your A, this is your B, this is your C. Here A equal to B equal to C. Suppose this is your alpha, this is your beta, this is your gamma. This angle is called alpha, this angle is called beta, this angle is your gamma. In case of cubic, here A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degree. Here we can able to form simple face, body. Simple means only the constituent particle present at the corner. Face means extra constituent particle present at the 6 faces of the cubic. Body means one constituent particle present at the center of the body. Like cubic unit cell, you can also think about the other type of unit cell, that is your tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral and hexagonal unit cell. You can just change the angle and length. You can able to form different types of unit cell. This is all about the three-dimensional lattices and their unit cell. Next I will discuss about the number of atoms per unit cell in a cubic lattice. In case of cubic, generally we think about three types of unit cell. One is your simple cubic unit cell, shortly it is called SCC. Then how many numbers of atoms per simple cubic unit cell? Look at that, this is your simple cubic unit cell. In this unit cell, 8 constituent particles are present at the 8 corner of the unit cell. Look at that, this constituent particle present at the corner of the unit cell. By this constituent particle, we can able to form 8 unit cell. This is your number 1 unit cell, 2, 3, 4, 5, 6, 7, 8. That means by this constituent particle, we can able to form 8 unit cell. From this it is clear that for one unit cell, these constituent particles have 1 by 8 part contribution. That means for the formation of this unit cell, the contribution of this constituent particle is 1 by 8 part. Remember this upper part cannot be used for the formation of this unit cell. That means we think about this part. This part cannot be used for the formation of this unit cell. So by the help of knife we can able to cut the upper part. It is not necessary for the formation of this unit cell. Next I will cut this part because this part is not necessary for the formation of this unit cell. Again I can also cut this part because this part cannot be used for the formation of this unit cell. Only this part is used for the formation of this unit cell, and this part is placed like this. Clear? This is the 1 by 8 part of these constituent particles. Here 1 by 8 part, here also 1 by 8 part, here also 1 by 8 part, here also 1 by 8 part. That means we can take 8 1 by 8 part for the formation of this cubic unit cell. For one constituent particle we take 1 by 8 part. There are 8 constituent particles present, so we can multiply here 8. That means the total number of atom per SCC equal to 1 by 8 into 8. That means 1 atom. That means the total number of atom per SCC equal to 1. By the help of one atom, we can able to form one simple cubic unit cell. This is your simple cubic unit cell. I can draw the 1 by 8 part of each constituent particle like this. Look at that. This is the diagrammatical representation of simple cubic unit cell. This part is present at each corner of the unit cell. This is your 1 by 8 part. There are 8 constituent particles present at the 8 corner of the unit cell. So this is your 1 by 8 part, and I can multiply the 1 by 8 part with the 8. As a result, the total number of atom for simple cubic unit cell is 1. Next I will explain about the number of atom for body centered cubic unit cell. This is your simple cubic unit cell, where an extra constituent particle present at the center of the body, then this unit cell is considered as body centered cubic unit cell. For the corner constituent particles, generally we take 1. That means there are 8 constituent particles present at the 8 corner, and each constituent particle have 1 by 8 part contribution for this unit cell. So here I can write 1 by 8 into 8 equal to 1. Now an extra constituent particle is present at the center of the body, so it is bound to add one extra constituent particle. That means there are 2 constituent particles is necessary for the formation of body centered cubic unit cell. So we can think that the number of atoms for body centered cubic unit cell is 2. Clear? This is the diagram for simple cubic unit cell. In case of body centered cubic unit cell, an extra constituent particle present at the center of the body of this unit cell. So this is the diagrammatical representation for BCC. Next, I will explain about the number of atoms for face centroid cubic unit cell. This is your simple cubic unit cell. When 6 constituent particles present at the 6 center of the 6 faces of this unit cell, then this unit cell is said to be face centered cubic unit cell. When one constituent particle present at the center of one face of this unit cell, then it has 1/2 parts contribution towards the formation of this unit cell. There are 6 faces, so here I can write 6 into 1/2 equal to 3. In the other hand, 8 constituent particles present at the 8 corner of the unit cell, and each constituent particle have 1/8 part contribution for the formation of this unit cell. So here I can write 8 into 1/8 equal to 1. That means totally 4 constituent particle is necessary for the formation of this unit cell. So we can think that the number of atoms for face center cubic unit cell equal to 4. This is your diagram for simple cubic unit cell. There are 6 constituent particles present at the center of 6 faces. So I can write like this. This is the diagrammatical representation for face centered cubic unit cell. Again I will repeat, the number of atoms for simple cubic unit cell is 1. The number of atoms for body centered cubic unit cell equal to 2. On the other hand, the number of atoms for face centered cubic unit cell equal to 4. This is all about the number of atoms for unit cell in a cubic lattice.